So again, sorry to start late. I have my reasons. I'll go over to make up for it, don't worry. So we begin with a word of prayer. Dear Father, we thank you for this day. Again, I thank you for this class and this opportunity we have just to meet and study your creation. Help us to glorify what we do and just to understand a little bit more about linear algebra today, Lord. In your name I pray, Lord Jesus. Amen. All right. So let us talk. Well, I guess first I'll just say, are there any questions? If there's a question or something, I can attempt to answer a question. If there are not questions, then I will go on. All right, so I want to talk to you guys about orthogonal complements and, Graham-Schmidt today. And I think to start with, we need to make sure we've got the basics down pat. And I think I've proved this before, but let's do it again. Let's just try to make this self-contained here. So definition, S, a subset of Rn, is orthogonal if we take x and y in S, and that implies that x dot y is equal to 0, right? So in other words, an orthogonal set is one for which the dot product of any two vectors in the set is 0, all right? Now, S subset of Rn is orthonormal if S is orthogonal and x in S implies that the length of x, which of course is the square root of x dot x, right, is equal to 1. Another way to say that more compactly is that if S is equal to, say, v1, v2, dot, 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 vk, then vi dot vj is equal to Kronecker delta ij for all I and j. Right, so the dot product of two vectors is either 0 or if it's 1 if it's with itself, all right? What do we know about orthonormal sets? I mean, we've proved this before, right? If S, a subset of Rn with the number of S equals to n and S orthonormal is an orthonormal basis. All right, we know that. An orthonormal basis is a basis which is orthonormal. Orthonormal bases are especially nice. Let's see here. So, theorem for beta v1 vn orthonormal if x is equal to the sum j equals, let's say I equals 1 to n of ci vi, then ci is equal to x dot vi. All right. So, can we prove that? Let's take a second here to prove that, because that's kind of a important idea. So, the proof looks like this. If we have x is equal to a sum I equals 1 to n of ci vi, right? Then if we look at x dot vj, what do we get? We get vi dot with vj, right? So there, technically I'm using the property of the dot product, that the dot product of the sum is the sum of the dot products, to bring the dot product inside the summation. So I am making a step there. But once that step is made, what do you got? Well, if it's an orthonormal basis, that's the Kronecker delta, right? And so what happens there? It's either what? It's either 1 if I is equal to j, or it's 0 otherwise. So the Kronecker delta is the natural enemy of the finite sum. It pretty much kills it. Although it leaves one person left over to go report to the enemies, as is traditional with a superior conquering force. Got to leave somebody to testify. So CJ testifies here. CJ delta 1, 1 is the only thing that survives from the whole sum. But that's exactly what we're trying to prove. See, that says that x is equal to a sum I equals 1 to n of x dot vi times vi. And in fact, that formula is worth kind of remembering in its own right. That's a better way to look at it. The components, right? The components of x with respect to the orthonormal basis, they're just given by dot products. Yeah? Another way to look at this, yet another way to look at this, is as follows, aka the coordinate vector of x with respect to the beta basis is what? The first component, x dot v1. The second component, x dot v2. And we could go on, x dot vn. Does this look familiar? It should look familiar. Think about calculus 3. How do you find the components of a Cartesian vector? What's the x component? X dot I. What's the y component? Y dot, the vector dot j, right? What's the z component? The vector dot k in the ijk notation, right? This is simply that same idea, but for a basis in n dimensions. We can calculate components by dot products. This is not generally true of all bases, right? This only works for orthonormal bases. So orthonormal basis, super special. We really like them, all right? So obviously, it would be a nice thing if we had some kind of procedure where we could take a basis which was not orthonormal and somehow make it orthonormal, right? So that's the next order of business here, is how to modify a basis to make it orthonormal. So, hey, let's start with a really stupid case. Number 1. If beta is orthogonal and non-zero. See, because 0 is orthogonal to everything, isn't it? Think about this. What is 0 not perpendicular? 0 is perpendicular to everything because 0 vector dot any vector is 0. But supposing beta is a supposing beta is an orthogonal basis, which means that it's pairwise perpendicular, but not necessarily length 1. How can we elevate this to a orthonormal basis? What do we do? So let's suppose the beta is v1, v2, vn. Can you guys tell me? Let me call this new. I'll call it beta tilde for lack of imagination. I want to make it u1, u2, un, where these are orthonormal. How should I proceed?
Divide vector by the length.
Divide each vector by their length. Right. Let ui equal to vi hat. in the parlance of like Calc 3, the normalization, like the unit vector, right? So that specifically is vi divided by the length of vi. Very good, that'll do it. So now the length of each vector is 1, right? Because you can check that that makes the length of ui equal to 1, right? Excuse me. Ay, ay, ay. Well, I mean, let's try it out. Here, how's this work? ui dot uj is equal to vi over the length of vi dot vj over the length of vj, if I take your construction, and I do. So that gives me vi dot vj divided by the length of vi times the length of vj. But what is vi dot vj equal to? It's either 0, right? Or if I equals to j, you've got vi dot vi over the length of vi squared, also known as 0 for I not equal to j, or 1 for I equals to j, also known as the Kronecker delta. So if you can prove that the dot product of two vectors in your basis is given by the Kronecker delta, then that proves it's orthonormal. Because that's a concise way of saying they're pairwise perpendicular and they have length 1. So yeah, we got it. Wouldn't it be lovely if every basis was orthogonal and this is all we had to do? Like, that would be easy, right? But it's not always that way, is it? So let's go on to case 2. Let's talk about beta basis for R2. Let's try to understand that. So we'll let beta be equal to, say, V1, V2. All right? That's given. This is given. And our goal is to create beta tilde U1, U2 orthonormal. All right? Now, I don't know, different instructors emphasize this less or more, but it should be talked about in Calc 3 that there's a picture we could draw here, right? So in terms of understanding how V1 and V2 relate, so let's see here, how can I put this? If V2 is like up here, and V1 is down here just for the sake of, a picture of it, right? First of all, how should I start? How about this? We use the idea we just used in the previous idea. Begin by normalizing V1. So let's put U1 equal to, V1 divided by the length of V1. Right? In other words, let's let U1 be V1 hat. Yeah? So we'll do that. Now then what? Well, a helpful thing to think about is the fact that V2 rather, can be written as a sum of two vectors, right? V2 can be broken into two pieces. The one piece is like this, right? The other piece is like that. So I call this the projection onto V1 of V2. I call this the orthogonal projection of V2 onto the V1 direction. Like the formula for the projection of V2 onto V1 is just V2 rather. V2 dot V1 hat times V1 hat. So what that does is it picks off the component of V2 that's in the one direction, and then it makes it a vector in that direction. A slicker formula for that without the hats looks like this. It's V2 dot V1 divided by V1 dot V1 times V1. And then the orthogonal piece, how do you get that? Orth v1 of v2, it's simply equal to v2 minus the projection in the v1 direction of v2. So what that does is it subtracts off the piece of v2 which is parallel to v1. That's the idea here. Of course, you can see this in terms of vector addition, right? The projection plus the orthogonal projection is equal to v2. So you can understand this formula by like tip-to-tail vector addition directly through, directly geometrically. Anyway, excuse me. The larger point here is that orth of v1 acting on v2 is simply equal to v2 minus v2 dot v1 divided by v1 dot v1 times v1. All right. So there's a stone cold formula for the orthogonal projection. That will give you a vector which is necessarily perpendicular to v1, right? Like you can check it. Check for yourself that orth of v1, v2 dot product with v1 is equal to 0. Work it out. Like, you don't have to write it down. Like, just look at it and think through this calculation. You should be able to see why it's 0. Like, look at it. When I take the dot product of the boxed formula right here, v2.v1 is v2.v1, right? But then I take the dot product of the second one with v1, which gives me v1.v1 divided by v1.v1. They cancel. It leaves me the numerator, v2.v1. So they cancel and give me 0. So this is by construction perpendicular. All right? Unfortunately, it's not length 1, right? So oftentimes I think of Gram-Schmidt, this process of how to modify a basis to make it orthonormal. That is the Gram-Schmidt algorithm. The answer to this question is the Gram-Schmidt algorithm. Sometimes it's helpful to take a sort of twofold approach. So continuing with 2 here, we can let's call it u1 bar equal to, or I'll put a prime on it. I'll make it a prime. u1 prime is the orthogonal projection of v1 in the v2 direction, which we just had a formula for. That was v2 minus, my bad, v1 dot v2 divided by v1 dot v1 times v1. So now then, if we looked at the set, like u might, I want to make this u2, my bad. I'm sorry guys, u2, 2. If we look at the set u1, u2 prime, this would be orthogonal, right? But it's not normal. See, because we need to normalize u2. So this is, not good enough. What we want to do is let u2 equal to u2 prime hat. Normalize it. All right, so like u2 prime divided by the length of u2 prime. Right? Then you'd have u1 and u2 orthonormal. So guys, there's a choices we have to make here in terms of computation. There are 2 ways to go down this path. All right, and probably the best way to do it. I don't know. I don't have a super large bank of calculations that are under my belt in terms of explicit calculation. I find that Gram-Schmidt actually carrying out by hand it's pretty intense computationally, which is part of the reason I've put this to this part of the course where you guys get more computer help, So here's the issue. Do I want to normalize as I go, or do I want to be content to create an orthogonal set, which then I can do like step 1 on? which is super easy, right? After everything's said and done, just normalizing a set, that's pretty simple, right? So what we could do, so here's a strategy. Number one, given, what am I calling the given? I guess I'm calling it beta. Given beta equal to V1, Vn, number two, we could create beta prime equal to, say, U1 prime, UN prime, right? Orthogonal. And then step three, normalize beta prime to get orthonormal. I guess I'm calling it beta prime prime. Whatever. My notation is not stabilized here by any means, guys. All right. I think usually once the dust settles and I have a moment to think about my life, I call the thing I'm starting with like prime prime, and then the middle one prime, and then the last one I take the prime off, because ultimately I don't want a bunch of ugly notation on this. This is the thing I want to use going forward, you know. But anyway. So let's actually put this into practice. Let's do an example, yeah? Excuse me. So, you know, when I test on this, I usually, you know, either keep the vectors super nice, so that, you know, doing a Gram-Schmidt on 4 things isn't too horrible, or I make it horrible, but it's only like a 3 by 3. So I do think students are quite capable of that calculation. I've tested it before. You guys have done it before. Example 1. So let's suppose we're starting with like 1, 2, and let's do 3, 4. That's my favorite, isn't it? So let's orthonormalize this thing. So I'm going to let I'm gonna do the normalized last thing, all right? So U1 prime is just going to be 1, 2. Then U2 prime is going to be, and by the way, this is V1, V2. So U2 prime is going to be V2 minus V1 dot V2 divided by V1 dot V1 times V1. That's the projection, the orthogonal projection, rather, of V2 with respect to V1. It should give me the perpendicular, should give me the part of V2 which is perpendicular to V1. All right, so that in particular is 3, 4 minus, I'll write it out here, 1, 2 dot 3, 4 divided by 1, 2 dot 1, 2. All times, 1, 2. All right, what do we got here? Well, we got 3, 4. I'll do that. I don't usually make a mistake there. What is 3 plus 8? 3 plus 8 is 11. What is 1 plus 4? 1 plus 4 is 5. So we've got minus 11 fifths times 1, 2. Now I need to think about fractions, yeah? So that's going to give me 15 minus 11 over 5 and 20 minus 22 over 5. Am I right? What's 4 in terms of fifths? It's 20 fifths, right? What's 3 in terms of fifths? It's 15 fifths. So that gives me, apparently, 4 fifths, comma, minus 2 fifths. There you go. That's my U2 prime. Now, how about just a quick check? Is that perpendicular to 1, 2? Try taking the dot product of what I just boxed with 1, 2. You should see you get 0. Yeah. All right. So, and let's see here. Great. So at this point, U1 prime, and of course, you know, so U1 prime, U2 is orthogonal. Seems like this will be the rest of the semester. I'm just be coughing the rest of the semester. Starting to feel like that. Let's see here. So, but there's not much semester left, so I guess it's not too bad. No, it's bad. This is not how I want to end the semester. So anyway, u1 prime, u2 prime is orthogonal, but it's not orthonormal, so we're not done yet. How do we normalize? Well, so let's see here. Beta prime prime. All right, so what's the length of, well, square root of 5, right? So I do 1 over the square root of 5, 1, 2, comma. This is an important comment. Please do not ignore this. When you're normalizing vectors with fractions, you pull the common denominator out. All right? Listen to me. You pull the common denominator out. Think about this. When I'm calculating u2 prime hat, I've got 1/5 times minus 4 minus 2 divided by the length of 1/5 times minus 4. There's only a minus on the 2. 4 minus 2. 4 minus 2. What can you do with that length? So this, if you ignore me on this, it will eat 5 minutes of your final. Literally 5 minutes of your final will be lost to arithmetic here. Because this issue compounds, like if you ignore it. See, you can cancel these. Normalizing a vector and normalizing a scalar multiple of the vector, it's the same problem. So be smart about this. Don't normalize the one with fractions. Normalize the one without fractions, 4 minus 2. After this kind of correction, I usually make a mistake. As you know, pride goes before the fall, that sort of thing. Let's see here, 16 plus 4 is 20. So I just do 1 over root 20 of 4 minus 2. And there you go. This is orthonormal basis. For R2. Now you'd say, well, okay, that's great, but I mean, if you're smart, or if you're just sarcastic, you'd be like, I already know an orthonormal basis for R2. Do you guys already know an orthonormal basis for R2? Like which one? I hope you do. Yeah? Very good. That's what I was looking for. The laziest possible answer. Yes, there are many others, but this is the Schmidt algorithm applied to that basis, though, okay? It's the Schmidt algorithm. Excuse me. So, that's just for 2. How about for 3? Let me do it in the middle board here. So 3, suppose you got beta equals to v1, v2, v3, all right? So what we're going to do is essentially start with beta prime is, u1 prime, u2 prime. The question is what to do next. We already know we're just going to, for the moment being, we're going to let u1 prime equals to v1, and we're going to let u2 prime equal to what? v2 minus v1 dot v2 divided by v1 dot v1 times v1, like we just did. All right, that's going to be our construction for the first 2. That will orthogonalize the first 2. How do I get the third, though? So here's how we're going to construct u3. u3 prime, we're going to let be the well, let's look at it in terms of operations. So what we can do is we can do orth. Let me leave myself. I'm going to leave yourself a little room to write here because there can be a thought process. Okay. So if we do orth in the excuse me, v1, and maybe we should let's to be truthful, we don't really care about v1, v2, and v3. Ultimately, it's what do we want the perpendicularity? We want perpendicularity of the new basis we're creating, right? So we should start thinking in terms of the new basis. So let's say, like, really, first of all, we want to get rid of the part that's in the u1 prime direction. So like orth u1 prime of v3. v3 is the thing we haven't used yet, all right? So like orth of u1 prime of v3, that is going to be perpendicular. That vector is going to be perpendicular to u1 prime. Is that good enough? Well, that's not good enough. We also need it to be perpendicular to u2 prime. So what do? Do it not once, but twice, right? So we just orthogonalize with respect to both of the vectors. All right. And when you, so what is that? Well, that is equal to, well, let me not derive this. We don't have that much time in here. So this works out to the following. It works out to v3 minus, oh, goodness gracious, v1 dot v2, v1 dot v3, rather, over v1 dot v1 minus v2, oh, my bad, or, sorry guys, I'll get it eventually, u2 prime dot v3 over u2 prime dot u2 prime. And if you start thinking about your life, you realize, oh, I really should have thought of this. It would have been better, actually, to see the pattern here. It probably would have been better for me to look at this in terms of the primes. So this is really v2 minus u1 prime dot v2 over u1 prime dot u1 prime. I regret my notation. In terms of putting primes on this thing, you know? It would have been much smarter for me to put primes on the original basis, so they had less primes, but you know, what's done is done, right? So u1 prime without. See, so then you can see that it's kind of always the same thing. So like, continuing this story, if we were to go past 3, and we were talking about the kth step, the kth prime step would be something like this, you know, vk minus the sum, let's say I equals 1 to k minus 1 of u sub I prime dot vk divided by u sub I prime dot u sub I prime u sub I prime. And so that would be the unnormalized Schmidt algorithm, which would produce for you perpendicular vectors. And where that's coming from is just doing subsequent orthogonalizations one after the other every time, getting rid of the pieces which are parallel to the previous vectors in your list. So let's actually put this into practice for my example 2 here. So suppose you've got, you know, beta equal to 1, 2, 0, 3, 4, 0, and oh, I don't know. What do you guys want? Anything? We can put anything we want here. Just don't make it. Just make it. The one thing we can't do is make it linearly dependent, like I did for case 1, right? I did have the remark there. I warned you guys. If these are not linearly independent, let me know. And you let me know. So it's good. So here, anything we like. All right, fine. 5, 6, 7, there. I'm pretty sure that's a basis for R3. So let's orthonormalize it. So I'm suggesting that beta prime, we're going to do just what we did before. 1, 2, 0, And then apparently, 4/5 minus 2/5. And then the question is, what do we do over here? All right, so there we're going to use the thing we just worked out. All right, let's do it. So my V3 is 5, 6, 7. And so U3 prime is V3 minus let me just write it out. We have the pattern right there. Okay, so V3 was 5, 6, 7 minus minus 1, 2, 0 dot 5, 6, 7 over 1, 2, 0 dot itself. That goes in the 1, 2, 0 direction. And then minus, and this is where it gets ugly, 4/5 minus 2/5. See, I'm starting to feel like a smart move would have been to get rid of the 5th, but I'm trying not to further modify my algorithm at the moment. There are various modifications of this algorithm. I think you've probably noticed that as you're working on your computer project, right? I think the main thing is whether or not you're normalizing as you go. I seem to have lost a 0 here. Yeah, that's not good. We can't take the dot product of a 2-dimensional with a 3-dimensional vector. That's generally frowned upon. There we go. Throw 0 back in there. Sorry about that, guys. All right, so what's that? That is a headache is what that is. Let's see here, 5, 6, 7 minus, we've got 5, 1 times 5 plus 2 times 6 is 12. 12 plus 5 is 17. 17 over 5 times 1, 2, 0 minus, what's that work out to? Let's see here. I believe we can factor out a 5/4 from that. No, wait a minute. I think we can factor out a 5. If I get rid of all the 5ths, think about it this way. I've got a 1/5 divided by a 1/5 times a 1/5, right? What is that? That is equal to 5. So let us forget about all the fractions except for the last one. Wait a minute. Oh, there's also a 1/5 upstairs, isn't there? Hey. So in other words, we can just ignore the fractions and just focus on the numerators. So 4 times 5 is 20. 20 minus 12 is 8. And divided by 20. And the fractions are dead to us because we did the arithmetic in the smart way. What's the not smart way to do this? Actually write out all the fractions and hope that you work them out correctly. You won't. Probably. I don't half the time, 3/4 of the time. Anyway, so there it is. And then we can simplify. How do we got that? So we got 5 minus 17 over 5 minus 32 over 20. And then we've got 6 minus 34 over 5 plus 16 over 20. And then finally 7. I guess I should have expected that, truth be told. So can you guys tell me what we get there? Or you want me to try to do it in my head and see what happens? What's 20 minus 4 times 17 minus 32? 4 times 17, 40, 68, 58, 70, 20, 70, 50. I'm probably wrong. Yeah, I'm definitely wrong.
Oh, 0.
What's-
First one's 0.
First one's 0? Dude, seriously? That can't be right. Really?
one's also 0.
Yeah.
What?
The first two have zeros for the third.
Double-edged term.
So the orthogonal is just
Sweet. All right. So, man, I should have expected that. I feel embarrassed. It's almost like I planned it to be this way. Oh yeah, I planned it to be this way. Isn't this cool? Yeah. Okay, great. So, you'll never know. So that's still not orthonormal, but at least this is what? Orthogonal, which is better than not. It's orthogonal, but not normal. How do we normalize it? Length 1, right? So the orthonormal basis we're looking for is, it starts out the same way, right? Like, where was I? You'll forgive me if I write it this way. 1, 2, 0 divided by the square root of 5. But I'll allow you the same luxury. Don't tell the other professors. Let's see here. Where was my second vector? 4 minus 2. And we divided by square root of 20, I believe. And this one is just 0, 0, 1. So there you go. That's an orthonormal basis for R3 that we've achieved by orthonormalizing. This is the Gram-Schmidt algorithm. And so when I say the Gram-Schmidt algorithm, it's kind of like when I talk about the Gauss-Jordan elimination algorithm, right? Is there a precise algorithm? Does it exist in a book in terms of precise steps which we could all agree on? You know, in terms of a precise pivoting procedure. There is such a thing, right, in certain books. In different books, you'll find a different thing, right? Do I dogmatically enforce you doing the algorithm in the particular way that I introduced it? No, right? You are allowed to do other things in the spirit. So similar comments apply here. There is a Gram-Schmidt algorithm, which is in my notes, which is built on repeated applications of the orthogonalization of the vector, right? But it starts to become apparent as you do these calculations that there are modifications which we could make which would make our life easier, right? Like if I was smarter, a modified algorithm maybe would have just thrown away the fractions and kept for myself a 4 minus 2, right? Like maybe keeping vectors full of full of integers, maybe of the correct dimension would be good, is a way you could go, right? Like since we hate fractions. Anyway, thankfully there's this thing called MATLAB, right? And if you want to do Gram-Schmidt on a set of vectors, you merely put those into a matrix and throw it to something called orth, as it turns out. Orth is the way to go. I found something called Gram-Schmidt the other day, but I can't find it now, so I guess it doesn't exist. You know, the problem is that there is an unending sea of computer projects from people who have other courses where they're forcing students to program their own native version of Gram-Schmidt to help them to learn how to program in MATLAB. I'm not trying to get you to learn how to program in MATLAB. I'm trying to get you to learn how to use MATLAB to achieve your purposes, yeah.
So does orth actually implement the Gram-Schmidt algorithm?
I have no idea, but it does create an orthonormal basis. That's a good question. Does it actually do Gram-Schmidt? I don't know, but it does Gram-Schmidt in the same sense that I'm allowing you to do Gram-Schmidt, which is do Gram-Schmidt-like things to create an orthonormal basis from a given basis. Now you might say, well, if you're finding a basis for Rn, you already know. My orthonormal basis for Rn is E1, E2, E3, E4, E5. Yeah? So you might say, well, what are you really saying? What I'm really saying, what's more interesting, is finding an orthonormal basis for a subset of Rn, where you already have a given basis. So let's talk about that. I don't know if we really have time to do it justice today. Well, I still have 5 minutes because I have 5 minutes late. So a space of 1, 2, 3, 4, 5, and 1, 0, 1, 0. next